Millions of bodies within the young Sun's nebula never grew large enough to become planets. They are now called asteroids. So their composition is determined by primarily three things: their surface reflectivity or albedo, their spectrum, and their density. And their types include the C type, which is carbon rich, the S type, which is stony in nature, and the M type, which is metallic in nature. The most prominent asteroids are Ceres, with a mean radius of 925 kilometers, which is considered a dwarf planet by the International Astronomical Union, on which surprisingly water vapor was discovered recently, and Vesta, which has been studied by the Dawn mission. So the collision rate between these asteroids, while not rare, is much lower than expected because of the way they are distributed through the main belt. So here you can see the distribution of asteroids in our solar system, with mostly Jupiter being responsible for the setup. The majority of the asteroids are concentrated along the main belt between the orbits of Mars and Jupiter, and Trojans and Greek families of asteroids are found on Jupiter's orbit at the Lagrangian points 5 and 4, 60 degrees behind and ahead of Jupiter along its orbit respectively. There are also some near-Earth objects, one of which may have actually been responsible for the extinction of dinosaurs from the Earth. So the next set of planets are the Jovian planets. Jupiter and Saturn are the traditional gas giants, and the ice giants are Uranus and Neptune. Jupiter and Saturn alone account for about 92% of the planetary mass of the whole solar system, which explains why they are called gas giants. So they usually consist of three layers, like the core, the inner layer, and the outer layer. The core is mostly rocky, theorized to be rocky, composed of materials like magnesium, silicon, iron, and nickel. And the high pressures near the core actually condense the gas into a somewhat liquid state, which makes up the inner layers. And the outer layers consist of helium and hydrogen and methane for Uranus and Neptune. So the depth of these individual layers actually tells us about the formation of these planets. And there is a vast difference between the core and surface temperatures, with the surface temperature of Jupiter being around 67 degrees Celsius, going up till 35,000 degrees Celsius at the core of Jupiter. This vast difference in temperature is due to the internal heating of the gas giants, which is the energy they give off in excess to the energy they receive from the sun. This, combined with the rotation of the planets themselves, gives rise to the distinct stormy weather pattern characteristic of the gas giants. Moving ions in liquids give rise to magnetic fields, which is evident in the case of liquid metallic hydrogen, which gives rise to such a strong magnetic field on Jupiter that it can be even detected on Earth itself. In the case of Uranus and Neptune, though, due to the absence of liquid metallic hydrogen, the magnetic fields are much weaker. Another shared characteristic of all the Jovian planets, though this may come as a surprise to few, that they all have rings or ring systems. But of course, none can match the grandeur or splendor of those of Saturn. Next, we come to Jupiter, the godfather of the planets. Jupiter is big. So big that it is 2.5 times of all the planets, asteroids, and comets in the solar system combined. In fact, if it were only 13 times bigger, there would be deuterium burning in its core, and it could be called a brown dwarf. If it was 60 times bigger, Jupiter would be a full-fledged self-sustaining star. Partly due to the heating caused by gravitational compression, Jupiter actually gives off much more energy than it receives from the Sun. Sometimes it can even manage to outshine the Sun in the radio wavelength. That means if you switched off the Sun, Jupiter would still be shining. On account of its strong magnetic field, auroras on Jupiter shine in the X-ray. as compared to the auroras in the visible wavelength, which are just pretty lights on Earth. Though up for debate, Jupiter has long been known as a cosmic vacuum cleaner, saving the inner planets from the continued onslaught of comets and asteroids. This photo captures the historical event of comet Shoemaker-Levy 9 crashing into the atmosphere of Jupiter, releasing energy equivalent to hundreds of nuclear bombs. This impact created Earth-sized blotches on Jupiter, which could be seen even through amateur telescopes on Earth. A lot of the material from the inner parts of Jupiter was thrown up into the upper atmosphere, giving astronomers a rare peek into the insides of Jupiter. The Great Red Spot, the most prominent feature of Jupiter, can also be seen here. A supercyclone big enough to fit 3 Earths inside it, it can have wind speeds touching up to 640 kilometers per hour. Though the reasons of the persistence of the spot since many centuries and its characteristic red color are still a mystery to astronomers. Jupiter is a planet with the radius 11 times that of Earth and with a day lasting only 9 hours. This gives rise to an impossibly fast rotation rate, which creates an amazing turbulence in the atmosphere of Jupiter. Some parts move faster than the others, which is the cause of the bands seen in Jupiter's atmosphere. However, these cloud layers are only 50 kilometers thick, with a lower denser layer of ammonia and a lighter layer of water vapor on top. There is no solid ground to stand on Jupiter. In fact, it is theorized that it may not even have a solid core. Overall composition of Jupiter is 75% hydrogen, 24% helium and 1% other compounds. Missions to Jupiter include the flybys by the Pioneer and Voyager missions in the 1970s. The Ulysses, Cassini and New Horizons mission use Jupiter to slingshot themselves to great speeds, up to 83,000 kilometers per hour in the case of New Horizons mission, which shortened its journey to Pluto by 3 years. These flybys provided evidence of lightning storms on Jupiter and also mapped the radiation belts of Jupiter. The orbiter Galileo made the first observation of ammonia clouds on Jupiter. Juno, which was launched in 2011 and which will arrive on Jupiter in 2016, will precisely map the magnetic and gravitational fields of the planets, and also will search for the presence of water vapor in the atmosphere of Jupiter. Jupiter's moons have been known to us since the time of Galileo. The 4 biggest moons that he could see on his telescope are now called the Galilean or Jovian moons. Ganymede is the largest moon in the solar system, bigger than the planet Mercury itself. It is said to have subsurface oceans too. Callisto is the farthest moon from the surface of Jupiter and has the most heavily cratered surface in the solar system. Io, Jupiter's innermost moon, certainly has one of the most fascinating atmospheric systems in the solar system. It gets stretched out by Jupiter's tidal forces so much that the molten material inside Io's core is forced to be ejected out of volcanoes about 500 kilometers above its surface. This material is soon swept away by the magnetic field lines of Jupiter to create a plasma stream that in turn causes lightning storms on Jupiter. The smallest moon of Jupiter is Europa, which is a prime candidate for hosting life. Europa has a very smooth surface as compared to other moons in the solar system, though it does have an elaborate system of cracks in its icy surface in which warm water is theorized to have life. Majority of Jupiter's 60 plus moons were in fact discovered after 1990. Most of the inner smaller moons are actually temporary systems which will be soon ripped apart by the tidal forces of Jupiter. These small moons also help maintain Jupiter's faint ring system. There is a lot of interest in exploring Jupiter's moons, especially Europa. But due to a focus on manned missions, NASA has dropped its Icy Moons Orbiter mission. And instead, this mission has been picked up by ESA, though with the proposed launch date in 2022 as opposed to a 2015 launch date for the NASA mission.
Next up is Saturn, the best dressed planet in the solar system hands down. Though primarily known for its spectacular rings, it's a pretty interesting planet by itself. First of all, if placed in an ocean large enough, it would float on water on account of its really low density. It is similar to Jupiter in many ways, with some notable exceptions. Due to a lack of metallic hydrogen as compared to Jupiter, its magnetic field is much weaker, comparable to that of the Earth. Being further away from the Sun, it does not receive enough energy for chemical reactions to produce colorful features in its atmosphere like Jupiter. Like Jupiter though, it does produce heat internally by the Kelvin-Helmholtz mechanism of gravitational compression. Concerning its structure, it is made up of a small rocky core surrounded by a thicker liquid of liquid metallic hydrogen, which is followed by a liquid layer of helium-saturated molecular hydrogen. The outermost layer consists of 1,000 kilometers of hydrogen gas. It also has very different poles, with the North Pole having a massive hexagonal storm and hurricane-like storms near its South Pole. A great white spot pattern can also be spotted about once in 30 Earth years near the time it reaches its equinoxes. Saturn's rings are made up of mostly ice and some rock. The ice content is the reason for their high reflectivity. These ice chunks vary in size from dust grains to large boulders. Despite having large structures, their actual thickness is quite less. Their combined mass is much less than the Earth's moon, and they cannot ever clump together to form a satellite for Saturn, even if they wanted to, because they lie within Saturn's Roche limit. Major rings are the G, F, A, B and C rings, and there are some gaps in them as well, mainly due to either orbital resonances with Saturn's moons or the presence of tiny shepherd moons like Pan and Daphnis, which give them their structure. Here is the cutaway view of the Saturn system that shows the inner and outer elements that we were talking about. The Frenkel line shown here may be an unfamiliar term, but it is just a point in temperature and pressure above which fluids, in this case mostly hydrogen, behaves like a gas, and a liquid below it. It may be helpful to pause here for some time to note the intricacies of Saturn's internal structure. Saturn's larger moons are quite fascinating. Here they are arranged in clockwise fashion in order of their distance from Saturn's surface. Known as the Death Star moon, the distinguishing feature of Mimas is a giant impact crater named Herschel, which is a third of Mimas' own diameter itself. It is Mimas that is responsible for the Cassini and NK divisions in Saturn's rings through orbital resonance. Enceladus is covered with water ice that reflects almost 100% of the sunlight that strikes it, and as a result of this, its surface temperature is extremely low, at about minus 200 degrees Celsius. With a geologically young surface, it has features like tiger-like stripes of fault lines and large geysers that release plumes of water, ice, gas and dust into Saturn's ring system to replenish, to mainly replenish Saturn's E ring. The next three moons, Thetis, Dione, and Rhea, are broadly similar types of moons, with all being heavily cratered and possessing complex terrain. Saturn's largest moon, Titan, is one of the most Earth-like worlds we have found till date. Its thick atmosphere and organic rich chemistry makes Titan resemble a frozen version of the Earth several billions of years ago, just before life started on Earth. It is also the only body in the solar system besides Earth with large bodies of liquid on its surface, in the form of methane-ethane lakes. Like Europa, Titan is also a leading contender for the discovery of life outside Earth in our solar system. Hyperion, Titan's immediate neighbor, is much smaller than even Mimas and is very irregularly shaped. It also has a very odd, like sponge-like porous surface. Iapetus is known as the yin-yang moon because its leading hemisphere is dark as coal and its trailing hemisphere is much brighter than it. The reason for this is still a mystery though. With respect to information about Saturn and its moons, Cassini has been an invaluable resource. One of the most complex missions ever launched, its development started way back in the 80s. It launched in 1997 and reached Saturn in 2004. And despite its original mission being only till 2008, it received 2 consecutive 4-year extensions to function till 2017. Some of its landmark events and discoveries include landing the Huygens probe on Titan's surface, which gave us color photographs of this alien world. It also discovered some of Titan's giant lakes, which are said to have more hydrocarbon reserves than all of the oil on the Earth combined. Enceladus went from being a relatively unknown moon to a prime focus for future missions to evaluate the possibility of life on it. Iapetus' long-standing mystery of its bright and dark surface was also solved. The hexagonal structure on Saturn's north pole was imaged in its entirety for the first time, and Cassini also reported a moon in the early stages of formation in Saturn's ring. Cassini has had certainly very impressive scientific results. Let's take a moment now to reflect on how far we have progressed as a species, with Cassini's version of Carl Sagan's famous pale blue dot photograph. It seems astounding to me that a civilization from a mere pixel of this photo managed to design a spacecraft sophisticated enough for what was perhaps the world's most wide-angled selfie. NASA had actually told people in advance that Cassini was going to photograph the Earth, so thousands of humans waved out at the exact same moment as this photograph was taken. Talk about an out-of-the-world photograph. Uranus is the third of the gas giant planets and the first planet to be discovered in the modern times. It is barely visible without a telescope, which is why it was not known to our ancestors. They may have confused it with a star. Uranus is a bit different compared to Jupiter and Saturn. It is an ice giant, and most of the planet's mass is made up of a dense fluid of materials like water, methane, and ammonia, along with hydrogen. It also has a small rocky core, which makes it different from Jupiter and Saturn. Due to Uranus being farther away from the Sun, its temperature is too low to produce the chemical reactions which can produce surface features like Jupiter and Saturn. In addition to this, the upper atmosphere is thought to have a high-level petrochemical haze that obscures features that are lower in the atmosphere, which is why we do not know much about Uranus. But perhaps the biggest mystery about Uranus is that its axis is heavily tilted. It almost barrel rolls about the Sun instead of orbiting it. This causes 20-year-long seasons in which either of the poles point towards the Sun, through which they get energy to form bands of storms in an otherwise featureless planet. Here you can observe how Uranus barrel rolls about the Sun. The degree of Uranus tilt is 98 degrees. Also, another thing to note about Uranus is that it has a faint ring system of about 13 rings, some of which were discovered only recently by the Hubble and Keck telescopes. Not much is known about the moons of Uranus because the only information we have about them is through the flyby they had from Voyager 2, but we do know for sure that they consist of more rock than ice as compared to Saturn's moons, and their names in order of their closeness to the surface of Uranus are Puck, Miranda, Ariel, Umbriel, Titania and Oberon. The ice giant Neptune has a surface temperature of minus 225 degrees Celsius, similar to that of Uranus, despite only receiving about 40% of the light Uranus receives from the Sun. This difference is made up by Neptune's remarkable internal energy heat source, which produces 2.7 times more heat than it absorbs from the Sun. So despite the surface temperature being so low, Neptune's core is thousands of degrees in temperature. This creates convection cells which, when coupled with the rotation of the planet, drives the fastest winds in the solar system, up to 2000 kilometers per hour. That's more than the speed of sound. Neptune's characteristic blue color is mostly due to a high level of methane in its atmosphere. And it is even theorized that at the core of Neptune, the pressures may be high enough to liquefy diamonds to create icebergs of diamond floating on diamond oceans. This is how Neptune appeared to Voyager 2 back in 1989. The Great Dark Spot was a megastorm the size of the Earth, where super high wind speeds were recorded. Other distinct features that Voyager 2 saw were the scooter, a white storm cloud on a higher atmospheric level, and a smaller dark spot. When Hubble observed Neptune again in the 90s, the Great Dark Spot had disappeared and was replaced instead by a larger number of smaller, darker spots in Neptune's atmosphere. Neptune has 14 known moons, though Triton is by far the largest. Its peculiar retrograde orbit around Neptune and large orbital tilt suggest that Triton was originally a dwarf planet captured by Neptune from the outer solar system. It probably has the coldest surface temperature in the solar system at just 38 Kelvin above absolute zero, and seems to have a geologically active surface with cryogenic volcanoes and nitrogen spewing geysers. Apart from Triton and the other moons, Neptune also has a very thin ring system, though it's much more like arcs than rings. These rings tend to clump together in some places, creating arcs of concentration rather than being continuous rings throughout. So here are the tasks we have for you this time. Think about ways in which we can deal with the threat of near-Earth objects. Explain the mechanism of gravitational assist in your own words. Explain the term brown dwarf. Describe what is the Roche limit, and envision a mission to the gas giants or its moons, and tell us about what will be the scientific value of this mission, and how do you propose to convince the NASA committee or NASA ESA or ISRO committee to actually go ahead with it.